All right. So the recorder is on. I got the mic going, and I got some good news. Okay, but it may or may not benefit you. But it's there in the long run. The department chair, one of the department co-chairs, talked to me yesterday about making a presentation to the other professors in the computer science department of how I do screen recording, the tablet, and stuff like that. So at least a few people were looking into doing in-class screen recording with the tablet and the whole setup. So potentially we'll probably be seeing more classes starting to, if not streaming, at least doing a recording. So I guess it's good news, okay? But it will take some time because what Larry said was he's looking for funding to purchase, the equipment. Yep. 2010, I do not have the full setup. I have my USB mic, which is just stationary. I only switched to this setup this semester. I purchased, all that stuff like mid-semester. And then the tablet, I got it, I think, last semester. So I've been using the tablet, since last semester, but not the entire last semester. Like the earlier part of last semester, I had a document camera. So it's just basically a webcam, and it records what I write on a piece of paper, and I echo it back onto the main screen. It doesn't work too well because when I'm writing, my hand is covering the entire screen, and there's also a refresh rate issue with that approach. But we are looking into, actually getting everything done the same way that I do right now, but using the workstation that are already here, because the software that I'm using, they're all cross-platform compatible, so there's no requirement to use Linux anymore. Well, there are reasons why I use Linux, but for one thing, I can keep my tabs and everything here. Okay, so what we'll do today, as I promised on Monday, is to revisit the homework assignment, but this time we will apply the A-star algorithm, and we'll also use two different sets of H values. One is not informed, which means they're all zeros, and then the other one is fully informed, which means the H value reflects the actual length of the shortest paths. So that's what we'll do first. When we have time left, we can talk about other things. So are there any questions before I start with that? No questions. Okay, all right, that's cool. All right. Okay, so what I'm doing right now is just to get back to the homework assignment from Monday, because I need to go back to the description of the graph itself, and then we start up the tablet, because then I can draw a picture. We can then represent it graphically. So we are looking basically into having an identical setup like what I'm using right now. For they're thinking about whether to do it per classroom or per instructor who wants to do it. So I can see it is more cost effective if it is just per classroom. So then we have a lockable thing somewhere in the classroom. We just put everything in the lockbox. All right. So, so this is 440. Okay. All right. So the first thing I'm going to do is really just to copy the graph onto the tablet. So this way we have a graphical representation. So 2 tabs. There we go. Okay. So we got 4 vertices. We got A, B, C, and D. D is the destination. And then we have the edge going from A to B with a cost of 1, A to D has a cost of 10. B to C is 2. Uh-oh. Well, I can still do it this way. And then B to D is 3. C to D is 1. And I think I capture all the edges. There are 1, 2, 3, 4, 5 edges. And in the picture, there are 1, 2, 3, 4, 5 edges. So I think I got all of those. And I'm just thinking, whether to make a copy of this now or do it later. I can always do it later. Okay, so now it's up to you guys. Do you want me to use a heuristic that is just uninformed completely, or do you want the one that is fully informed? Start with uninformed. Okay, so that's easy. So we'll define the heuristic function, and we really only have to define the heuristic function to the destination. Okay, so even though the function itself is supposed to be defined between any two vertices, the only ones that we need are the ones to the destination. But in this case, it's okay. It's really easy because we say for all VW in uppercase V, H of VW is just 0 because we are saying, okay, we do not want the heuristic function to be informed at all. Okay, so making them all zeros means they are not informed. They're not going to tell us, they won't give us a clue of where to explore first. Okay. Do you want to go use the spreadsheet approach to trace the algorithm, or do you just want to work it out on a piece of paper like this? I can do either way. Trace, no trace, trace. Okay. Too many choices. Text, stop giving us choices. What grade do you want? A, B, C, D, or F? You guys got it easy. Because in Hong Kong, they have A, B, C, D, E, F, G, and H. And F is fail. So F, G, H are all failing grades. So you have barely failing, you definitely failed, or you totally sucked. Yeah. I have no idea. Well, that's in when they were still using the British system when I was graduating from high school. What they do now. Okay, I'm just going to be lazy and kind of use this as a template. So all I need to do is to copy the first row, well, actually, I can do this. I can copy everything and then just delete the portion that I don't want, because if I copy everything, it maintains the width as well, which is handy. So I'm just going to delete the rest that I don't need, get rid of those, and that's good. That's a good starting point. And then we magnify that a little bit. And then we have to go back to the algorithm, because I don't want to just recall the algorithm from my head. I just want to make sure that I follow the algorithm step by step. So we go to graphs, and it's the last portion of the notes. There we go. Okay. So now we got everything here. That's what I've been doing at the lab. Okay, there we go. So we'll go ahead and separate this as its own tab, so I can just alt tab into this screen a little bit easier. All right. So as far as the previous is concerned, it is a function where everything has an undefined previous vertex. So we have A, coming from undefined, B coming from this part. I can just basically copy and paste, because every graph starts with the same thing. And then D also has a previous of undefined. So this is basically a set all by itself. Hi, Ron. Oh, okay, sure, no problem. Okay, so the g function and the f functions, one is the length of the actual shortest path known up to this point. The other one is the estimated length of the shortest path from the start vertex through this particular vertex to the destination. So I just want to remind you guys the meaning of each function. So as far as g is concerned, because we have not explored a single thing, so from A to the destination, we'll say at this point it is infinity because we don't even know whether it's connected or not. Same thing for B, same thing for C. But for D, it is a little bit different. D is just 0. Because remember, G of D is the length, known shortest path from vertex D to the destination. But guess what? D is the destination. So the length of the shortest path from the destination to itself is 0. The path doesn't have any edges. Okay. And then F is almost the same, but not exactly. I'm just going to do a copy and paste. But it's not exactly the same. Well, it is exactly the same in this case because it is asking if I go from vertex D through vertex D. No, if I go from the start vertex. Okay, so this one is not the same because we do have to. It is the same because the heuristic function is 0, but only because of that. Is that okay? Or not? Are we buying f of d is 0? In other words, according to what we know about the graph at this point, the length of the shortest path from vertex A through vertex D to vertex D is 0. But then you go like, but how? We know that the cost or the distance to go from vertex D to vertex D is 0. What about the estimation from vertex A to vertex D? That's 0 because we said we don't want our heuristics to be informed. So the heuristic, the h function, is always returning 0. That is why f of d is 0. All right, so the set O starts with the start vertex, which in this case we have to pick one. Dijkstra's algorithm does not need, or at least the way that I use Dijkstra's algorithm, does not need a start vertex. So it's up to you guys. Pick one. Which one do you want to be a start vertex? A. Okay. Okay, we'll pick A then. So we just have to write it down here. A is our start vertex. Okay. All right. So back here, we just have to say, well, we only have one single vertex in big O because that's our start vertex. Are we good so far? Okay. So now we can actually enter the algorithm itself. And let me see which one has the algorithm. I think it is this one. Yep. So we enter the algorithm. The algorithm says, okay, we're done with all the initializations. So the algorithm actually starts here. As long as big O is non-empty, and there are vertices in V such that blah, 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 do the following. So at this point, vertex A is inside, and the question here is, g of x is a 0, and f of v is infinity, because we don't know whether there's a path or not. Okay, let me double check. F is initialized to infinity. Yep. So I think I mentioned that this part has to be modified a little bit. Do you guys remember that from Monday? Because according to this, we really, we're going to fail this condition because it says, for all v in V, f of v is less than g of x. X is our destination, and at this point, g of x is, okay, I might have done something incorrectly here. Yep, I did it wrong. Okay. Do you guys spot the error? This is the result of me not following my own algorithm and thought that I remember. Yeah, I flipped the destination and the origin. This one is actually infinity. The one that should be 0 is this one. And then the same thing over here. So that means in the test, do not try to say, yep, I remember the algorithm and just kind of go by that. Because I flipped it. I flipped the destination and the source in the initialization. There we go. Now it makes a lot more sense. Because g of a is the length of the known shortest path from the start vertex to that particular vertex, not to the destination. I just flipped the direction of everything. And the f function is telling you the estimated length of the shortest path from the start vertex through a particular vertex to the destination. So that's why both of these are zeros at this point. So I do apologize for that because I messed up. I forgot. Is that okay? Did everybody understand where I made my mistake? It has to do with the initialization, this part here. I just did not follow my own instruction. Okay? All right, so everything is good now because now we can say that, oh, okay, there's one vertex in V, in O, in big O, that has the f value less than the g value of the destination. Because when you look at the spreadsheet, f of a is less than g of d. So both conditions of the loop is now satisfied. So we now pick a particular vertex. We have no choice but to pick A. Okay, let me just make sure this is the right notation. Yep. So we pick A, and then we remove A from big O. And then we have to look at all the outgoing neighbors of A. If it's Dijkstra's algorithm, we look at all the incoming neighbors. When it is A star, we look at all the outgoing neighbors. So according to the graph, the outgoing neighbors of A is B and C. Oops, A and D. It doesn't really matter which one you pick first. So which one do you want to explore first? You want to explore B first? Okay, so we can do that. So we explore B first, so that means we are picking vertex B as the variable n. Then we have to compute the value of t here. The value of t is asking, if we start from the start vertex, going through B, and then go to the destination, what is the estimated length at this point? Okay, what do you think that's going to be? What is the distance of the edge AB? I think it's 1. What is the heuristic of going from B to D? 0, because all the heuristic function is going to return 0. So 1 plus 0 is 1, so we have 1 as t. And then in the algorithm, it's looking for a condition. The condition is t less than the g value of vertex B at this point. Vertex B at this point has a, okay, let me do it one more time. We're checking against the g value. Okay, so the g value of vertex B is infinity, is 1 less than infinity. Yep, okay, so we have to go through the conditional statement. So when we go through the conditional statements, we make updates to all of the items in the trace. So the previous set is now updated because now we have to remember, according to what we know as the shortest path at this point, the previous vertex of B should now be A. So now this is updated. We also have to update both the G and the F values. So the G value is saying in order to go from the start vertex A through B to the destination, the length of the shortest path from A to B is 1. Okay, that's pretty easy because that's the only edge connecting A to B. And then the F value is based on that, and then the value for B is basically T. T has a value of 1, so we just put that 1 here. But we also have to remember to add the vertex B to big O, because now since B is changed, so everything that connects to B or connects from B, everything that B connects to can potentially be impacted. So that's why we are adding B to the set of big O, so that we remember to re-explore everything that B connects to. Because if B is getting a shorter estimate, then everything that B connects to can potentially be impacted. Is that okay? We have one more vertex that A can reach directly, and that's vertex D itself. So now we have to compute the T value. According to the algorithm, the T value is based on the G value of vertex A, which is 0, plus the distance between vertex A and vertex D as an edge. And that particular edge has a distance of 10. Okay, so we are looking at 0 plus 10, which is 10. So now we go back to the trace, and then we update this thing to be 10. So the question now is okay, so let's go back to the condition. So the condition is asking, T is 10, is it less than the G value of N? And in this case, N is vertex D. What is G of D at this point? It's infinity. 10 is less than infinity is true. Okay. So that means we have a whole bunch of updates here. So once again, we update the previous, so that at least at this point, we basically say in the solution graph, vertex A is right before vertex D. And then we also have to update the G and also the F value. The G value is updated to 10 because the G value is the length of the shortest path from the start vertex to this particular vertex. It just so happens to be the destination, but that's the definition of the G function. And then the F function has exactly the same value, because this time it is because D is a destination. So that's also updated to a 10. And then we have to add vertex D to the set big O, because that can potentially impact every vertex that D connects to. Now D is a destination, it doesn't really connect to anything else, but that really doesn't matter. We still have to put it into the big O set. Are we doing okay so far with this? At this point, we are exhausting all the outgoing neighbors of A. So now we have to pick one element out of big O and ask, okay, which one has the smallest F value, which means it is the most promising vertex on the shortest path. Okay, so out of these two, B has the smallest value. So we pick B, and then we take it out of the set. Now we have to look at all the outgoing edges from B. Sorry? Oh, okay. B only connects to D, so that's only one thing that we have to look into. And then we have to compute the value of T first. The value of T, once again, is G of B. G of B is 1, plus the distance of the edge connecting from B to D directly, and the distance of that edge is 3. 1 plus 3 is 4, so T now has a value of 4. And then we ask the question, is 4 less than the current G value of D? Okay, let's go back to the algorithm just to be sure. So right here, the condition is asking whether T, which now has a value of 4, is it less than the G value of, in this case, D, because D is the neighbor? So going back to the trace, G of D is currently 10. So is 4 less than 10? Yep. Okay. So we need to do some updates. Copy and paste this. The previous of D is no longer A. Instead, it is B now. And then we also have to update all of these items so that we know that the G value of D is now 4. And then the F value of D is also 4. Like so. And because of that, we are going to, because we just updated the G value of D, we have to put D back into the big O set. But guess what? It was there to begin with. So that's why we are not seeing any changes on row 7, because the set already had D as a part of it. Okay? So we go back to the beginning of the algorithm, and then we say, okay, do we have anything else that we can choose at this point? Well, the destination vertex is in it, so we'll go ahead and pick it. The condition of here, basically says, if we fail the second condition, we can stop also. The second condition says, if every single vertex for every single vertex of V, uppercase V, f of V is less than G of X. X is vertex D at this point, which has a value of 4. So we are basically looking for things that have a smaller f value than 4. And if you look at all the f values, some of these still looks, kind of, it's still pretty low. So we still continue with D. We pick D as C at this point. Vertex D has no outgoing edges. Okay, let's go back to here. You can see that D has no outgoing edges. So we are done. We remove vertex D from the set. Oops. So the set is now empty, and we're done. Yep.
What about the other outgoing edges
From B?
Yeah, like C.
I thought B only had one. Oh, okay. I forgot about that. I forgot about this edge. Okay. We're not done yet. Never mind. Okay, get rid of this. So now we have to explore the other edge, okay, which is C. So we have to add the edge, the distance of the edge BC to the G value of B. The G value of B is 1, and then the edge has a cost of 2. Okay, so I forgot about that entirely. Thank you. 2 plus 1 is 3. And then the condition is we have to compare 3 to the G value of vertex C at this point. The G value of vertex C is infinity. 3 is less than infinity is true. So we have to do some updates here. So we say the previous of C is now vertex B. And then we also have to update the G value of C, which is going to be just 3. And we also have to update the F value of C, which is also going to be 3. That has to do with all the heuristic functions, or all the heuristic values are 0. So this is also just 3. And then we have to add C, vertex C to the set. So the set now has C and D both as elements. Thank you, I forgot about that edge entirely. So when we get back here, we're not done yet. Okay, so we have to look at the vertices in big O, C and D, and pick the one that has the least F value. So when you look at C versus D, C still has a lower value, so we pick out C. And then we look at all the outgoing edges of C. The only outgoing edge of C is 1, which is going from C to D. And the T value of... Sorry? Oh, right. Once we remove it, we have to take it out of the set. Thank you. and then and now we have to compute the value of t, which is based on the g value of c, which is 3, plus the cost distance of that edge, which has a cost distance of 1. 3 plus 1 is 4. So now we ask the question, is 4 less than the g value of the destination at this point? The g value of the destination, g of d, is 4. 4 is less than 4 is false. Okay, so there's nothing to update at this point. So now we go back to the beginning of the while loop. We pick d as the last element. And then we empty the set. Yep. But since d has no outgoing edges, so there are no vertices to explore at this point, then we go back to the beginning of the while loop. The set is empty, and we're done. So is that okay? Okay, so the next one is going to have informed heuristic functions. So we'll go with that one. And the way to do it, I'm going to do it is to copy and paste all of these columns to a new sheet. So this way, I'm preserving the formatting. And for the most part, I can keep the initialization except for one value. So we'll get to that one when we get all the h values done. All right, so getting back to here, we have to define the h value from a to d, the h value from b to d, everything from whatever vertex to the last vertex. Okay, so technically speaking, we have d to d as well, but that one is always going to be a 0. What is the length of the shortest path from a to d? Just if you eyeball it. A to d has the shortest path has a length of 4, right? 4. There are 2 paths, but they're both 4. Okay. So the heuristic function in this case is fully informed, which means the heuristic function is in fact the length of the shortest path. Okay. What about from b to d? What is the length of the shortest path from b to d? That's an easy one. It's just 3. Yep. Okay. What about from c to d? That's an easy one. All right. So now we have a fully informed heuristic function because the heuristic function is actually returning the length of the shortest path to the destination. Okay. But it also means that when we initialize the f values, it is not the same anymore this time. It has to do with, for the initialization, the g value is okay. The g value is still getting a 0 for the start vertex, but the f value of the start vertex is now the heuristic value from the start to the destination vertex. So in our case, a is the start vertex, d is the destination vertex. So h of ad would be the f value of a. Is that okay? And exactly what is the h value from a to d? It's a 4. Okay. So in our trace, we are going to change that one. Just that one needs to be changed. So f of a is now 4. Sorry? No, not d. Because a star algorithm starts from the start vertex. So unless you touch a particular vertex, you assume that it is not reachable, and therefore the f value is infinity. Yep.
So function f is pretty much g of a plus h8 to x.
Correct. Yep, that's right. For every single vertex, it is like that too. Yep. Okay. So we're ready to start. So we have no choice but to pick vertex A to start with, and vertex A has 2 outgoing edges, right? Vertex A has got B as a outgoing edge and also D as an outgoing edge. Okay, it reaches these 2 by a single edge. Which one do you want to explore first? We used B last time. Do you guys want to use D this time? Okay, we'll use D this time. Okay. So we have to first compute the t value. The t value is still computed the same way. The t value is based on g of a, which is 0, plus the distance of the edge AD, which has a distance of 10. 0 plus 10 is 10, so t is going to end up with a value of 10. The comparison of the conditional statement is asking whether t, which is now 10, is it less than the g value of d. The g value of d is infinity. 10 is less than infinity is true. Okay, cool. So we'll just put it here, and we'll do this one update. Oops. We have to do a bunch of updates because we have to first remember the previous of d is a. In other words, the currently known shortest path is just going from a to d directly. And then the g value is 10 because the length of the currently known shortest path has a length of 10. And then the f value is also 10 because the heuristics of d to d is 0. So that means it is the same as the g value. The f value is the same as the g value. Are we doing okay so far? Okay, we have to add vertex d to O, like that. Any questions about this? Okay, now we go to the other outgoing edge. The other outgoing edge from A is going to B with a distance of 1. Okay, we know that t is 1, and then we ask the question, is 1 less than g of b? G of b right now is infinity, so the condition is true, so we have to do a bunch of updates. The previous of b is a. The g value of b is 1. So far, we haven't really changed the behavior of the algorithm. Now we change. How should we update the f value of b? The f value of b is based on the g value plus the heuristic value from b to d. What is the heuristic value from b to d? It's 3. 1 plus 3 is 4. There we go. Are we doing okay so far? Now we have to add b to the set as well. So db are in the set. There are no other outgoing edges from A, so we are done with the for each loop. Then we go back to the beginning of the while loop. So at the beginning of the while loop, we are now saying, okay, we got two elements in big O, B and D. Which one has the smallest value? B has the smallest value. Okay. So we pick B, and then we ask, okay, tell me what are the outgoing edges of B? It has an outgoing edge to one to D directly, and the other one to C. Which one do you want to explore first? Last time we explored D first. You want to switch the order and go to C first? Okay. So let's go to C first. So now we have to compute the t value, which is the g value of b, which is 1, plus the distance of that edge bc. The distance of the edge bc is 2. 1 plus 2 is 3. So t is 3. So now we have to answer the question, is 3 less than the current g value of c? The g value of c is infinity. 3 is less than infinity is true. Okay. So now we have to update all of these columns. Oops. Undo. Copy and paste. The previous of C is now B. And then the G value of C is just what T is, which is a 3. But the F value is the G value plus the heuristic. What is the heuristic value from C to D? It's a 1. So 3 plus 1 is a 4. And then we put C into the set. Oh, I forgot to remove B here. So now we have D C left in the set. And then it also has a destination of, it also has an edge going from B to D. So now we explore that particular edge. G of B is 1. What is the distance from B to D as an edge? From B to D is 3. Okay. So 3 plus 1 is 4. So T is 4. So now the question is 4 less than the current G value of D? D. The current G value of D is 10. 4 is less than 10 is true. Okay, so the condition is true, so we have to do a bunch of updates. So we go here and then we change the previous of D from A to B. Is that okay? And then we change the G value of D so that it is going from 10 to the T of 4. And we also want to change the F value of D from 10 to 4. And then we have to add D to the set, but it's already there to begin with. It's okay, we'll put it back in. Is that okay? B has no other outgoing edges. We have explored both of the outgoing edges of B already. So we are going back to the main loop, the while loop. At the beginning of the while loop, we are asking, have we found the shortest path? So technically speaking, we have found the shortest path already, okay? But the condition that I set up with the conjunction, that one needs to be thrown away. So we're going to have to look at D and C and explore these two and ask which one has the smaller value. Well, they are the same. You can see that the F value of C is 4. The F value of D is also 4. Okay? So in this case, you can pick one to explore or the other. It doesn't really matter. So at this point, the algorithm will still go, for a little bit longer, but it's not going to change anything at this point because the length of the shortest path of 4 is already determined. So the condition is not going to trigger anymore. Right. But we can still go. We can still follow the algorithm. It's just that it's not going to do anything. It depends on how the algorithm is stated. If you stop here, you have to explain to me why you think it is okay to stop here. But how do you know that? But how do you know that? Say that one more time. It is the length of the shortest path that is correct. But the algorithm doesn't know that. Because if you stop here, you have to tell me in general what makes it okay to stop here, regardless of how. Let me finish. Regardless of how H is defined. Okay, go ahead.
So we could say we're done here because it's pointless to go on because we won't find any short path on this.
But how do you know you cannot find any shortest path? Because you have to explain it using function f, function g, yep.
There is no f that is shorter than g of b.
That is true. So there's nothing that looks more promising at this point. So let me just repeat what Eric said. Okay, Eric said, if you look at all the f values, f of g of d, okay, which is the actual length of a known shortest path, is 4. Okay, so we know that already. Okay, so any path that is, we need a path that is shorter than that. Okay, but when you look at all the f values, well, tell me what are you observing about the f values? They're all 4s. Okay. What is that telling you? Remember, what is the meaning of the f value? It is an underestimate, right? It's an underestimate of the length of a path from the start vertex through whatever vertex you choose to the destination. But it is an underestimate, which means the actual length of a path through a vertex to the destination is at least 4. Is that okay? But we found a path to vertex D that has exactly a length of 4 already. So there are no shorter path available at this time. So if you explain to me in that way, then I can go, yep, you understand the algorithm, you can stop here. Yep.
So you can say there is no shorter path than the estimates. That's the right answer.
Say that one more time.
So there is no shorter path than our estimates in them.
So if the f value of everything, of all the other vertices, is at least g of the destination, then you can stop. Which in this case, it satisfies that particular requirement. Yep.
So in the algorithm, the condition will fail that's checking for any f values that are less than the g of the destination.
Say that one more time.
Like in the algorithm, you know how there's a condition that's asking if there is any f values
Mhm.
less than g of the destination.
Mm-hmm.
Then
That stay in the algorithm. That's a stay in loop condition. Yeah. So you're talking about this portion. Yeah, this is a part of the conjunction, which means if you cannot find a vertex in V such that f of V is less than g of x, then you can get out. Because the this condition has to be true to stay in the loop. So that means this condition still makes sense, except in some cases it doesn't. In some cases you can get out already, but this condition is still true, which makes you stay in the loop a little bit longer. Is that okay so far? Yep. To the spreadsheet? Yep. Yeah, I think what you're thinking is, but there are values smaller than g of 4, but these are all g values. We have to use the f value to compare against g of the destination. Yep.
I think I was looking at that line before.
Oh, okay.
And then so, for some reason, I was comparing F of B with W of D was.
Okay.
But you should compare F of C and
Right.
W of D because Y was pushing.
Okay, so let's say I don't stop here. Okay, I'm forgetting about the second condition of the loop. In other words, I'm completely forgetting that we got this part. Okay, and I continue with the loop, the while loop. The question is that going to be incorrect in the sense that it will find me a path? It would state a path that is not the shortest as the shortest. Can it make that mistake? Or is it just going to burn up a little bit more processing time, but no harm is really done? What do you think? Why? Okay, so if you think that continuing with this loop is not going to mess up the shortest path that we have found already, why do you think it is not going to mess it up? It has to do with the conditional statement. So you look at the conditional statement and tell me why at this point this can no longer be true. So let me just repeat what we know already so that you can formulate your logic and argument. So what I'm saying is, in the while loop, I'm totally forgetting about the second condition. In other words, the second condition is false already, but I'm not stopping. Okay? So the question is, knowing that every single vertex in V has a f value that is greater than or equal to g of x. Okay? Knowing that already. What happens to this condition? And why is it always false?
They will be equal.
Hmm?
The value of t will be equal to value of.
Okay, but these are all f values, right? They're not g values. And over here, we are talking about g values. Because t itself is the g value of c, which is the length of the actual known shortest path to a particular vertex c, plus the distance of the edge cn, okay? And we are evaluating whether that can be a shorter path. So why can we say that this can never become true, anymore? There is a relationship between f values and g values. What is that relationship?
F value is the G value plus E.
Yep. No, not exactly that. Okay, so if I want a closed form, g of some vertex v, it is the f value of v minus the heuristic of v to x. That's the relationship between the heuristic, the g, and the f value. Is that okay? And I'm claiming that every single f value that we know at this point is greater than or equal to g of the destination. Okay, so let's work this out a little bit. Okay, so f of v is g of v plus h of vx. Okay, and we are claiming that every single f value is greater than or equal to g of x. So what does this have anything to do with that condition? Okay, let's switch back to the algorithm. Why can't this be true anymore?
Can you repeat the previous question?
Okay, sure. So the question is, I already know that every single vertex has an f value that is greater than or equal to the g value of the destination. That is a given. I already tell you that. And because I totally ignore the second condition of the conjunction in the while loop, I'm ending up here. Okay. The question is, why can I guarantee that even though I ignore that condition, it's not going to mess up the shortest path that I have already found? So indirectly, what I'm asking is, why is this condition t is less than g of n? Well, let me pose it this way: can I conclude that t is less than g of n cannot be true anymore at this point, now that I know all the f values are greater than or equal to the g of the destination? Okay. This is the first time I think about this problem too, so because this is how I prepare for a test, or this is how I think about things, is what if I keep going, because intuitively speaking, it shouldn't mess up the shortest path. So if it doesn't mess up the shortest path, it means it's not updating the previous. Okay, if it's not updating the previous, it means it is not making other changes as well. So it pushes the logic back to that condition has to be false. So I'm going to switch back to the tablet, and we'll see if we can apply some logic here. So we know that this particular thing is greater than or equal to g of x. That's a given, okay? Because I'm telling you all the f values are greater than or equal to g of x. X is the destination already. So what can we do about this? I'll think about this a little bit, and then when I come to the actual conclusion, I'll let you guys know. How about that?
You'll tell us, and you're going to ask us
Huh?
as an exam question.
No, I'm gonna tell you. Hmm?
An announcement on Canvas.
Announcement on Canvas probably followed by a YouTube presentation. But you can think about this a little bit too. I know you guys have other final exams to worry about. Hmm. But there's something here that really should be able, that is provable, that we can keep going and it's not going to do any update to mess up the current shortest path. So, but I've done whatever I said I would do already. This part is kind of like a bonus part. And, okay, I just went to the wrong window. Okay, there we go. All right, so I have already done what I said I would do on the other day. And where's my spreadsheet? Right there. Okay, so the contrast is between this one versus this one. This is using, sheet 2 is using a heuristic that is that's not informed. I'm going to rename this one and say that, uninformed heuristic. And then this one, sheet 3 is a fully informed H. And you can see that in this case, it doesn't make that much of a difference, because, it's this one has one more exploration and the other one does not. But that's only because the graph is relatively small. And when the graph gets, increasingly complex and bigger, a fully informed heuristic will guide you to the shortest path a lot faster than an uninformed heuristic. Because otherwise, why would we have A star algorithm when Dijkstra's is already done? Yep.
It seems like with the informed one, you don't have to empty the set because of the second condition, and that way you'd avoid revisiting vertices.
Mm-hmm. Because when you look at the, okay, where is the algorithm? I'm looking for the question. No, I'm looking for the algorithm. Because the only time H comes into play is here. It's when you update the F value. In other words, what the H value is doing is if you have a good H function, a heuristic function, the F values are more realistic. So that when you pick an element out of O, based on who has the smallest F value, it becomes more realistic. Your greedy algorithm is actually saying, yep, I know who is the most promising. And what seems to be the most promising is actually the most promising. When your H function is not informing anything, like when it is 0, then what you think is the most promising is really just, most promising at that time, but, it's not really actually the most promising. Is that okay? Any other questions about A star and Dijkstra's algorithm? Yep.
The heuristic function give like realistic information, like not totally wrong, but
Okay, so let me ask you to clarify when you say, mistake or, misleading information, is it still admissible? In other words, is it still non-negative, and is it still an underestimate of the actual length of the shortest path? Yes? Okay. So let's work with that. Okay. So that's a good question, and I think you guys can work this one out. So what I'll do is I'm going to change the heuristics so that it is as misleading as possible, but still satisfy those two requirements. One, it is greater than or equal to 0, and 2, it is less than or equal to the length of the shortest path. In other words, I'm going to pick some value between what we have here, 4, 3, 1, and 0, and 0. But we'll make it as misleading as possible. Is that okay? All right. So I'm going to change this one to a 0. I'll change this one to a 0.5. Change this one to a 1. And this one cannot, I can't really do much about that one. Is that okay? So the heuristic values are now exactly opposite in terms of the original ordering. Is that okay? And then we'll see whether this actually does anything to the search algorithm. Do you guys want to go with this one or kind of do it one more time, but using the most misleading heuristic function? Because it's not just 0. 0 is just totally not telling you anything. This is telling you something. It's telling you to go try the wrong way. It's trying to mislead you as much as it can. Is that okay? All right, so let's try this one out and see what happens. We'll add another sheet here. This time I'm renaming the sheet first. Rename. And I'll call this misleading H. Okay, it's as misleading as we can possibly make it. And then we'll copy and paste out of this stuff. Over here. Get rid of the stuff that we think we might not need anymore. And this one, the F value, there will be a 0 here. Is that okay? And then we pick A out. O becomes an empty set. We explore the two outgoing edges. One is B and the other one is D. We'll pick B first. This part doesn't change, okay, because the G value of A is still 0. And then 0 plus 1 is 1. 1 is less than infinity is still true. So we are still doing exactly the same thing as last time. So in order to get to B, we want to go from A. So we are going to change this to A. The new G value of B is 1. That hasn't changed. But this time, here we make some changes, right? Because the heuristic from B to the destination is now changed to something that is misleading, or supposedly misleading. And what was that? From B to D is 0.5. Okay. So it's going to be 1.5 because it is the G value plus the heuristic value. So it's 1.5. Okay. And we still have another edge going to D, okay, which makes T 10. And we still have to go through the same thing, updating the previous of D to be, whoops. To be A. The previous is A. And then the G value is 10. The F value is 10 as well because the heuristic from D to D cannot be anything other than 0. All right. Is that okay? So far so good? Oh, I forgot about adding those to the set here. There we go. Okay. So now we have B and D in the set. We have to pick the one with the smallest F value. And when you look at the F value, B still has the lowest F value. So that part hasn't changed. The graph that we have is too small so that the effect of uninformed, fully informed, and totally misleading doesn't make that much of a difference. So we still have to pick B, which leaves D in the set. And B is going to D and C, okay, D, C. When it goes to D, G of B, which is 1, plus BD is what? 3, so it's 4 here. 4 is less than 10 is true, right? So this part still hasn't changed. In other words, I don't expect that we will see a lot of changes just because the graph is so simple. So this is updated to 4, and the other one is going to update to 4 as well. So we have, oops, no. Want to copy from here to here, and then change this to a 4. So this part still hasn't changed. Going to C is going to update because I have not been to C before. So the edge going to C has a cost of 2. This is 3. And we have to. Sorry? Yeah, we have to do that too. But we also have to update this one. Well, D is already in the set, so it doesn't do much here. But over here, we have to update the previous of C because we are going to C through B. So B becomes the previous of C. And then the G value of C was infinity. Now it is just 3. So you can see that it doesn't really make that much change compared to the previous one, just because the graph is too simple. This one does change too, I think, because the heuristic from C to D is 1. So now we have 3 plus 1, which is 4. Is that okay? And we have to add C to the set. So now we have to pick one out of these two, D versus C. And you can see that they still end up with the same F values. So there's not much we can do. It still ends up the same way, basically. Is that okay? Any other questions related to Dijkstra's algorithm or A star? Yep, go ahead.
Write out exactly what E of DSX would be, like after you solve this then. Just like the solution edges, like.
Say that one more time.
Could you write out what the solution graph would?
Yes.
That would look like?
Yeah. So the solution graph. I think I forgot to update A. Oh, the previous of A is still undefined. That's fine. So when you write out the solution graph, it is really looking at these things, but in a backward manner. So you have to add the edge BD, BC, and AB to the solution graph. This one is not really representing an edge because the start vertex is undefined. So basically, when you read the previous function backwards, that becomes your E prime, except for the undefined. The undefined is just not going to be an edge.
Also, so like if we look at the feature of the graph itself,
Uh-huh.
like BC is an edge that's part of the solution edges, but
Yes.
it's not really useful. Right?
It is not useful. That is correct.
Okay, that's
Yep.
okay.
Because it is not along the path from the start vertex to the destination vertex. So if you do end up with a solution graph like this, the way to track the actual shortest path is to start with the destination. So you go from D to B, and then B back to A, and that's your shortest path. So any other edges that is not used is really just there, but it's not useful. So it's not like Dijkstra's algorithm where it gives you a tree that represents the shortest path of every single vertex to a destination. This one is specific to a start vertex. Okay, any other questions? No other questions? It's all good?
All good in the hood.
Hmm?
All good in the hood.
Okay.
It's a lie. There's actually some serious socioeconomic problems in the hood.
And just locally to yourself at the end, finally, all Canada. And then the inside.
Well, this is not too bad compared to IB exams, right? Some of you has gone through the IB experience. How many years did they? The exams are about material over how many years? What is the span of time? 2. Okay. Yep. So this is only one semester, right? All right. Any other questions? We got 5 minutes left of the entire semester. We have 5 minutes of lecture time. Yep.
Wait, so to clarify that, so the exam's going to be about A star and A star only, or is it going to be other stuff?
The theme is A star. I think that's the best way to put it. Is it has an A star theme.
Use like relations and proof by induction and contradiction, I assume.
Oh, proof by induction can potentially be there. Okay, so let me ask you this question: what is proof by induction? What do you have to know?
Base case.
There's a okay. So the essence of proof by induction is the theorem has to hold true over a range of values. Okay, so that's the first thing you have to kind of look at the problem and go like, does it fit into proof by induction? Okay, is the theorem applicable to over a range of values? And the answer is yes. Okay, good. The second question is that range of value discrete? Now, everything that we do in this class is discrete, meaning that it's not continuous like in calculus. Okay, second requirement. So in proof by induction, you have to find a base case. In other words, you look at the range of values and you just say, I'm going to pick that one as my base case. Now, typically, the value that you pick as your base case is on one extreme end of all the values. Okay, so if you have natural numbers, 0 would be a good natural choice. Okay, if you have integers, both positive and negative, then you have 2 subproofs to do. One to start from 0 and go positive, the other one to go from 0 and then go negative. Okay, but 0 would still be a good choice, as a base case. Yep.
What do we go from like negative to 0?
No, from 0 to negative values.
Okay.
Yep. Because the first case, the base case, has to be a specific known value. Now, the base case typically is very easy to do because what you do is just plug in n equals to 0, and then you prove the theorem does work for that one single value that you choose for the base case. Okay? But you have to state it. You have to make it very clear, this is the base case, this is how I prove it. Okay? The induction step has 2 things, 2 components. The first component of the induction step is the assumption, the induction assumption. The induction assumption typically goes like, the theorem holds, let's assume the theorem is true for the case of n equals to k. Okay, you just have to state that. Then the induction step, the actual proof, is to say that, okay, making that assumption, now I can use that assumption to prove that the theorem is also true for the case of n equals to k plus 1 or k minus 1, depending on which way you're going, right? And that's it. That's proof by induction. Is that okay? Now, in some cases, it may not be a particular value k that you're adding 1 to or subtract 1 from. It can be a particular set. Okay, so you can say this particular set is, I can prove that the base case is the empty set. Okay, if this theorem holds true for the empty set. Then the induction step can say, let's assume that the theorem is still true for a set with this many elements. If I add one more element to the set, can I prove that the new set with that one extra element would still satisfy the requirement of the theorem? So it can kind of go in that direction too. Okay, that's proof by induction. So proof by induction is not really a very specific topic that can stand on its own. It is just a technique that you can use for a lot of different things. The second one is proof by contradiction. What is proof by contradiction in general?
It can't possibly be wrong.
What? Say that one more time.
It can't possibly be wrong.
It cannot possibly be wrong. That's the essence of it. But what are the steps? If I say that I need you to prove something by contradiction, identify the theorem first. Okay, tell me what is the theorem, then negate it. Okay, after you negate the theorem, where do you go?
You and it to your set of known true theorems.
Exactly. So things that are known to be true or that is given to you that is true, you use a conjunction, you attach the negated theorem to that thing, and then what do you do? you try to get to a contradiction. Now, resolution is just one way, okay, to get to a contradiction, but proof by contradiction does not require resolution. It's just one mechanism that you can use to get to a contradiction. Yep.
What would be another one? Just offhand.
You can use a truth table. You can use a truth table to look at the, for every single row, it is a 0. Okay, you have all the given facts. You have the negated theorem. You have the gigantic conjunction between all of these things. For every single row, the expression should give you a 0, should give you a false. That is how you get to a contradiction.
We have to do any other fancy proofs like contrapositive.
Nope. Contrapositive is not a proof technique, is it?
Don't you find one, or is it counterexample? The one where you find the counterexample.
Counterexample is a proof to show that the theorem is not.
Oh, right, it's false.
Yep. 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 Because to prove something is not true, you just have to say, I find one single instance that this theorem does not hold true. Well, guess what? That makes the theorem not true. Because most theorems have an implicit quantifier that we typically just ignore or forget to mention, which is for all. So if you can find one single case where the theorem is false, then the for all part is falling apart. So that's why you can use counterexample to prove a theorem is not true. So those two can still be in the test. Functions would still be in the test because we just used functions.
What about relations?
Relations can still be in the test. So you still need to kind of brush up on relations. The one thing, counting, may still be in the test because in the sample test, there's a question of a fully connected graph. How many edges are in a fully connected graph. That sort of thing. So those are techniques to help you kind of figure out the number of things. So that's why it is still important.
Cardinality.
Oh, cardinality is part of everything that you know about set would still be important. The only thing that is kind of standalone that I kind of go like, maybe, maybe not, is resolution, because resolution and conjunctive normal form is specific to propositional logic. It's not like I cannot make connections between propositional logic and graphs. It's just that I have to kind of stretch it out a little bit to make that connection.
Let's not do that.
I cannot make any promises. Recommendation noted. How about that? And recorded.
Already coming up with the ideas.
Okay. So any other questions? Yep.
The test day, just to be clear. So it's from 12:45, right?
12:45 to 2:45 on next Monday. Yep. Pacific time. Because I don't want someone to come, a few hours later and I thought it was Hawaii time.
Oh, man. What state are we in again?
Or somebody coming like a day before or 12 hours early and think, I thought it's Hong Kong time.
This is the West Coast? Oh, man.
Okay, so any other questions? Nope. All right. Now, I still have office hours tomorrow and also on Monday. The office hour on Monday is right before the test, so that can be handy, right? I mean, I cannot remember. Probably 11.
It's normally at 11, so it's
Yeah.
at 12:45, so your office hour would be between
Yeah, let's say it's 11, and I will be in the design hub. Yep. All right. And tomorrow is a Thursday, and my office hour is also from 11 o'clock. And then on Friday, it is also from 11 o'clock. Well, I cannot remember how I set it up. It's next to my cubicle, on the wall. So, is that okay? All right.